Okay, we're very happy to have Oliver Janssen from EPFL. He's telling us about prior inflation from the gravitational path integral.
Okay, all right. So, yeah. This is based on a lot of previous work, most of it not my own, going back all the way, I guess, to the 80s. So let's get started. First of all, thanks a lot for the invitation. It's really great to be back. It's working. Okay. So this is the outline. I was going to start with a broad introduction. I'm not sure how much details will go, but introducing the idea of inflation. This talk is about inflation in the end. Reviewing, so we get on the same page with notation and about the flatness problem and about CMB anisotropies. Then the motivation for the work that we did, which is the question like, is there a theoretical prior on inflation models? We have a lot of inflation models. Is there any way to choose between them from a theoretical point of view? Then our approach to this is to prepare initial conditions for inflation with a gravitational path integral, which, although we don't completely understand it, still could be useful. Then this gravitational path integral will involve saddle points which are complex space-time metrics, and I'll discuss a criterion to select healthy, good saddle points and distinguish them from bad ones. It's not anything that's on completely firm footing at the level of a proof, but I'll discuss some features and drawbacks of that. And then I'll apply that criterion to these saddle points that we get in with this by trying to prepare initial conditions for inflation. And we come to some interesting surprise. Okay, so this talk is about inflation. So it's this is for the broad audience. So it's a period of accelerated expansion. It's a conjectured period, but it's our best guess to explain several puzzles with the hot Big Bang model. Okay, so just to get on the same page, because I'll be using very similar equations for the rest of the talk. So we're going to consider a homogeneous and isotropic universe with this metric, where this space sigma is a symmetric space. So it can be either a sphere, a flat, or it can be a hyperbolic space. So the curvature is -0 or 1 for hyperbolic, flat, or sphere. And in this universe, we're going to put some matter radiation and a cosmological constant. So the equation of motion that governs how the size of the spatial slice changes with time is this Friedmann equation, where here we put the density of the various forms of matter that we have. So here there's radiation that looks like 1 over the volume with 1 over the volume times 1 over with an additional factor of length. Then there is the matter part, which just dilutes like the volume, and then there's the constant piece, cosmological constant. This piece is the curvature. Okay, so how this can be rewritten is you can multiply this by 1 over h squared. So h is 8 out over a, and we can rearrange it into this form. Okay. And sometimes that's written as this equation, 1 minus omega is omega k. And now you can measure the various parts of rho. We've done that. And you find from this equation that right now, that's what the 0 is that this omega k is quite small. Okay, and now what's the so-called flatness problem? Is the observation that this quantity, this ah squared, is actually increasing as we go far enough back in time. Okay, just because this is the same equation rewritten a bit differently. If you now take a smaller and smaller, at some point these things are going to start growing, and so this ah is going to grow, and this omega k is going to decrease. So this is roughly the rough picture of what it looks like. So this is the evolution of ah squared. Here we're right now, so roughly 14 billion years after the Big Bang. There was a period, so now we're in according to current observations, we're in a period of dark energy domination again. This was until about this went back, if you go back in time to around 9 billion years after the Big Bang, then it transitioned into matter domination here. During this time, not much happened. This is a transition region, so this ah squared didn't change by much. It slightly increased. If we would go more into the future, it would start exponentially expanding. Dark energy would take over, and this ah squared would start increasing again exponentially. So with a rate h given by proportional to the dark energy density. So before that, we had matter domination. So here the thing this AH squared really starts increasing, and the curvature decreases, and then irradiation goes like 1 over time. And here I just draw, I went back to BBN, which is of the order of a second. This T equality is matter radiation equality. Okay, so that's the picture that we have. I didn't choose BBN for any reason, just some early time. And so now when you plug in the values, the observed values, you get that this thing was at BBN, let's say, quite small. You can trust the physics more. You can go back in time, it would scale linearly with that. So if you go to, let's say, 10 to the minus 12 seconds, this would become 10 to the minus 30. Now, of course, you should ask, why is this a problem? Is this really a problem? So, for example, the answer to that is not, well, I would have expected this to be some order 1 number at BBN.
For example, lambda is also very small at BBN.
Yeah.
Nobody cares.
And yeah. So it's right in the
Right?
United States.
Lambda at BBN is also
is
strongly
extremely-
subdominant.
That's right. Yeah. So I'm actually criticizing the fact that it's a problem. So
Okay.
yeah, it's supposed to be. So of course this couldn't have been order 1 because then we wouldn't be here to observe that. So it wouldn't make no sense. It would increase and the structures wouldn't have formed. So, but in any case, whatever you think of this, the point is that inflation, what it does is provide some mechanism to make this thing very small. Okay, so independently if this is a problem or not, what inflation does is it gives you some way to make this small. And the way it does that is already suggested by the picture we had before. We have, if you look at the very late times, there's this exponential increase. And so what you do is you paste an exponential increase onto it in the past, and this will do the job. So if you then go back in time, this exponentially decreases, and it can be as small as you want if the inflation lasts long enough. So here inflation happens at some high energy scale, h little h, while this is h naught, they're different. Okay, so that's just the basic mechanism. Very broadly, hopefully simply explained. So now these are, okay, so how do we get inflation? Well, one of the many ways to do that is with a scalar field. So that just looks like the same equation as we had before. Now the energy density supplied by a scalar field is just giving kinetic energy and potential energy. Same equation. And now when this phi moves slowly, so you can neglect the kinetic piece, this behaves, and this is not changing much. You see that this behaves like some high energy scale, and it causes an exponential expansion. So that's one of the ways you can change it. And then, so how to think of this thing is you can think of it as a Newtonian particle moving with friction, a friction proportional to the expansion rate h. So it's just Newton's equation with friction. And then you can also check that it's consistent to drop the acceleration and also the kinetic energy when some conditions on the potential are satisfied. So when basically the thing is very flat. Flat meaning this. Okay. So this is the picture we have. We have some potential energy density. This is a flat region, and there's a particle rolling down with friction. Nowadays, of course, we have a much more precise motivation for inflation than this flatness problem, which may not, depending on how you look at it, may not be a problem. So it can describe actually the origin of the detailed characteristics of the CMB anisotropies. So there's a picture from Planck, and relatedly explains the origin of gravitationally collapsed structures in the universe. Just a very rough picture. Spent one minute on that. It's just how this happens roughly is during inflation, perturbation of the metric and the inflation field. They behave like 3 fields, so they're oscillating until their wavelength. Their physical wavelength grows with time because this is increasing, and at some point it exits the horizon radius. And when the wavelength becomes larger than the horizon, which is 1 over h, then the thing exponentially goes to a constant. So it remains frozen when it's outside the horizon, and then much later, when the universe has gone into the radiation and possibly even matter domination period, they come back into the horizon and start oscillating again. So the idea is that the CMB temperature and polarization anisotropies, they're sourced by the modes that exited the horizon quite a bit before the end of inflation. So roughly 50 to 60 e-folds before the end of inflation, meaning an e-fold means this. Okay, the scale factor is increased by a factor of e for 1 e-fold. So the idea is that the statistics of the CMB anisotropies, they are set by the details of inflation. Okay, so now I want to come to two parameters out of many that we use sometimes to to describe the characteristics of and statistics of the CMB anisotropies and of inflation, the so-called scalar spectral tilt and the tensor to scalar ratio. And these things, they characterize the power spectrum of fluctuations in the metric. So there are scalar type fluctuations, which are parameterized by the scalar zeta, and tensor fluctuations. These things have a 2-point function and a power spectrum described by this kind of form, where this ns is the deviation from scale invariance. So if it was 1, it would be scale invariant. And this as is the amplitude of these fluctuations. This amplitude is, the square root of this amplitude is related to the size of the temperature. Right? It's altropies of order 10 to the minus 5. I forget all, I didn't write factors of 2. Now there's a similar formula for the temperature for the tensor modes, and there's also some amplitude, and the ratio of these two amplitudes is what we call this tensor to scalar ratio, R. Okay, so I wanted to introduce these two things. Now, how are these related to the dynamics of inflation? Well, you can show that the amplitude of the scalar fluctuations goes like h squared over epsilon, where epsilon is this, it's a slow roll parameter, and the tensor fluctuation is directly proportional to h squared. So this means that this tensor amplitude, it measures the energy scale of inflation, proportional to h. H squared is like v, so it's the energy scale of inflation. And r, the ratio of these two things, is proportional to epsilon. Okay, now, when we plug in the observed value for as based on the magnitude of the temperature fluctuations, we get this formula for the energy scale of inflation, which can be written in this way. So it's a very high energy scale, okay, quite close to the Planck scale. And it's multiplied by this factor, r. So we put in this value because we've measured that. And we know roughly that r is bounded, so these are some constraints that we get from CMB measurements. And r is bounded by this roughly 0.036. So there's going to be more, this is going to be measured better in the future. This Japanese experiment should measure it to level 10 to the minus 3, so it will be further constrained. Okay, so now this is getting towards the motivation of our work. So it's really easy to predict these specific features with models of inflation. Okay, so maybe you could say it's too easy because here are a bunch of models that people have come up with which, depending on who you talk to, they prefer one model over the other. But the point is that there's many of them. So okay, so these models 1 through 8, they have these potential. The details of this are not that important. There's different models of inflation, different potentials with tunable parameters. Here you have this f, here mu, q, and so on. And in each model, the parameter is varied in some interval. For example, in these monomial potentials, you can take the power to go from 1/2 to 7/2, let's say, and then you would scan over this model 8, which goes roughly in that direction as you increase p. And then the horizontal direction is how many e-folds before the end of inflation you assume that modes for this relevant to the CMB exited the horizon. So somewhere between 50 and 60 e-folds. That's what defines this width. Same for all these other guys. So this model is the cosine phi over f model. As you increase f, you go in that direction. If you increase it very much, you get back to here, which is the same as the quadratic equation. Okay, so the overall scale, this doesn't enter in slow roll, but you fix the overall scale so that you get the right amplitude of temperature. Okay, so here are the models versus observations. You see that there's many models, 2, 3, 4, 5, 7. They all kind of still fit the data pretty well. So there's many models, and again, depending on who you talk to, you'll have a different answer for which is the best model. So it's quite easy to get this. And not only that, but coming up with some model, so drawing some potential v that fits this data and all the data that we have from inflation is very easy. Okay, especially since these observations of the CMB they're only sensitive to a finite region of v. So as long as you preserve this more or less, you'll get the same answer, and you get this different answer. Okay, I'm not saying that makes much sense, but you could, just from that point of view, it's easy. Furthermore, if you look at the current observations, this may be just a personal point of view, but it doesn't look like if we measure these values, it's not going to necessarily tell us what the mechanism behind inflation is. It might inform us of some details of this potential, assuming that it happened via this potential-driven inflation. There's many other ways to get inflation. Measuring this won't necessarily tell us exactly what inflation was. If we measured it maybe exactly here, you could maybe argue differently, but it turns out, yeah, so that doesn't seem like able to us. So, okay, so now come to more like more motivation. So, a more insightful approach than just this function fitting, of course, is, for example, to study explicit UV models that give some. So these are well-motivated models that give concrete inflation effective field. For example, by studying axion effective field theories and some compactifications of string theory that we understand to a decent degree, which happens to be what we're doing with Matt, Cami, and Naomi. But apart from being quite hard, we believe that many of those inflation models, in the end, many possible inflation models are going to come from string theory, although we don't understand, we don't have full control over them all. But in the end, we believe that there's going to be a large collection of those, and also a large subset of them that will fit the data as well. So, also that probably won't tell us exactly what the mechanism is behind inflation. On the other hand, there's also a general belief that not everything goes. Okay, and in the context of quantum gravity, this falls under something called the Swampland program, okay, which says that not every inflation model, one of the things that it says, okay, is that not every inflation model can be UV completed into a good theory of quantum gravity. For example, you should have no large field excursions because then the EFT is going to break down once the field traverses a super-Planckian distance.
So who's our minister?
Excuse me?
Is a real our, or is you are collaborating with someone? Say our motivation.
Our for this talk, let's say. Our motivation for this. My motivation for this talk.
Your
Yeah.
You don't want to be part.
Yeah, I'm not speaking for you. Yeah, our motivation for this work. Yeah, and so in effective field theory without gravity, though, this you could say this goes under the name of positivity bounds, which have a long story, and that's actually what I talked about last time when I was here. But they were only kind of recently extended to theories of perturbations that spontaneously break Lorentz symmetry. And right now it's unknown what they imply for the EFT inflation, which I think would be a very interesting thing to look at. So the question is there some theoretical prior on this zoo of models? Can we put order into the zoo? Are there some initial conditions for inflation that are preferred over others, or maybe you can theoretically rule them out? Okay, so the methods that I just mentioned, you can study it from the top down. Let's say some string inflation, but that probably won't give you the answer. We can also study it from the bottom up.
Can I make a question?
Yeah.
Among the two you proposed, they were not totally arbitrary, right? I mean, 7 looked like some.
They're not totally arbitrary. Yeah.
Risky model or something like that.
Yeah, they're not arbitrary, but there's some smooth.
No, but
functions.
my question is, those that you proposed, meet the Swampland criteria?
Most of them, yes, because they they predict
Excursion.
not necessarily exactly super Planckian, but they but they're not. They don't have a very large field excursion because R is small. Typically, but it's not sharp. Yeah, some of those models that fit the data could still have could still be of order. Of order of Planckian distance in space, so that they're parametrically ruled out. So then, the approach we'll take here is via the gravitational path integral, which is a different approach. I'm not sure where to put it. So the idea here is that we're going to consider a time slice of some inflation history, right photon field rolling down, for a closed universe. So we'll consider k equals 1, which has some size a, and it's covered by a scalar field phi at some point. Okay, so you can place a surface anywhere you want in this inflation history. It's filled with phi, and then it has some size a, which you can also choose. Okay, and we're going to assume that there's an amplitude for this slice to occur at some point in the history, which is given by psi, the wave function of which has these values, which has these arguments, and the probability that it occurs is proportional to psi squared. So if the psi is a semi-classical state, then also the momenta are fixed to a high accuracy, and so then you can view this as the probability of initial conditions for classical evolution because we fixed the positions and the momenta.
Isn't it what Vilenkin has done like 50 years ago?
It's this. It's the same. It's the same. And Hurdle and Hawking. It's the same. It's this idea. But we're gonna put one new ingredient, and it'll.
But it's the same creation from nothing.
It's
right?
the same creation from nothing. I'll draw the pictures.
Oh, okay.
Yeah, indeed. But the thing I'll talk about should apply to the Vilenkin or Hurdle Hawking proposal, but they should also apply more generally. So there'll be a part of the talk which can be applied, should be applicable to any other proposal.
As I thought Vilenkin and Hawking are on opposite sides of the debate. Okay, you will talk about
No,
it
indeed.
probably.
I'm not going to go into this debate in detail, but you'll see what I mean.
Okay.
I think. Okay, so so the proposal that will follow is that, and again, not the whole talk will be contingent upon this, but just the important part will. So we're going to obtain this this amplitude in the semi-classical limit. We're going to take the semi-classical limit. That's the only one we'll consider, and so this amplitude is obtained by integrating or by summing over geometries which have no other boundary. So this A phi lives on a boundary of some space where you have, which is filled in by a metric and a solution to the equations of motion, which matches onto this boundary at some time. Okay, and the weight is given by the classical.
Oliver,
Yeah.
Should I think of A as the like a proxy for the number of e-folds that inflation should last? It's how
Not
large
necessarily
the
yet. It's just the size of the slice. So it's not telling you anything about what the history towards the past looks like. You could immediately create this, for example. We won't, but
By size of the slice, you don't mean scale factor of the universe.
I mean scale factor of the universe, but I'm not implying anything about how it got there. So it's not like not yet. Yeah. But yeah, it's the.
But for you, A is not even a scale factor, it's the true size of the universe,
Yeah,
right?
it's the
Because
true
it's a
size.
sphere.
Yeah. So, right. Yeah, but I'm not, okay. We haven't gotten to yeah, we'll get to this. So, okay, we're going to assume that it's given, the point is also we don't exactly know how to define the gravitational path integral, but we're going to assume that as G Newton goes to 0, it's dominated by some collection of saddle points. Okay. Okay, it's certainly not the only possibility, okay, and there's reasons to doubt it, for sure, but there's some generality to this thing. You can apply it to many models without, and it doesn't depend, like the procedure doesn't depend on the details. You don't have to go reformulating it every time. And there's also some mathematical elegance to this, so there's, so as Hawking would have said, the boundary conditions for the universe are that there are none. So it's at least interesting to look. So we'll be particularly interested in putting this boundary at here, okay? Where we take the scalar field to be at the end of inflation. So this is when the kinetic terms and the acceleration become important. We're going to put the boundary here. And we'll consider a scale factor A, which is much larger than the Hubble. Okay, so now we ask ourselves, what's the probability for this slice? So I'll just draw it like that. Okay. And here's how you obtain it. So now I'll describe what the saddle points look like. And now we'll come to, now these saddles do look like they had a period of expansion, which lasted for some amount of e-folds. So roughly what it is that you can imagine this is at the end of inflation, so you go back in time, and you evolve this data with the slow roll equations. Slow roll equations are first order, so only the values matter.
Is it just quantum mechanics in 2 dimensions, right?
Yeah, but
Only A and phi and nothing else.
only A and phi, nothing else. So in principle, the equation that we're solving is this Wheeler-DeWitt equation, h psi equals 0. So it's not really quantum mechanics, but it's h psi equals 0.
Right, it's quantum mechanics with prescribed value of energy or something like this.
Yeah,
right?
so without time, if you wish, it's h
Right,
psi
right,
equals
right.
0. And so this the Hurdle-Hawking proposal is a specific solution to this one.
Right.
Just specific, not all solutions. We're not doing. Yeah, they single out one solution, which should be generated by a classical solution, which looks roughly like this. So, and I'll describe more exactly what it looks like in a moment. But the rough picture is that you fix some big slice here. You go back in time via first order slow roll. So to first degree, it's just a real solution, and it decreases in size. Okay. And you go back until the time that A reaches a border 1 over h. So A was much bigger than 1 over h here. Now go back in time until it reaches roughly, and I'll be more precise, roughly order 1 over h. At that time, you make a transition into imaginary time, And why do you do that? It's to put this solution on a manifold with only one boundary. This is the only boundary. To do that, you go into imaginary time. Here it looks roughly like a sphere, which caps off smoothly at some point. And then you glue these two things together. So you get this. This is the picture, rough picture of what the solution looks like. Now let me go in a bit more detail. So in terms of equations and in terms of complex time plane, our metric is like this. Okay. And the contour that we're going to take in the complex time plane looks like this. So we make some imaginary time evolution. Then we go up into real time along the real axis.
So, sorry, can you explain more carefully what's the reason for complexifying time?
It's because the reason is that we want to put you want to put this. You want to write a metric on a manifold with no.
If you complexify time to compute some path integral by going into whatever, you complexify just to compute something by analyticity or something. But what exactly?
It forces you to go in here. Well, sorry. And you could if you. You could write this differently.
Why all of a sudden you allow yourself to go into complex time? What's the?
Because I'm looking for a saddle point which lives on some space with only one boundary.
Because you are saying your potential just dictating you that
Yeah,
there is a
there's
true
only one-
saddle point at complex plane.
Yeah, and the manifold is a ball. Okay, so we have a ball. You
Okay.
can view this T as R. Okay, so it's just a ball that has one. The boundary is a sphere.
So it's not arbitrary. It's the true
it's the
saddle
only-
point. Okay.
Yeah, it's a true saddle point. It's a full solution to the equation of motion. Has no singularities. And that's why.
And this is like actually a saddle point as opposed to like a maximum or minimum, or
Ah,
because
we
there's
call
some.
we say saddles. No,
It's
I don't
stream-
talk about that
it's
because
stream-
it's gravity and then
Right.
there's
But-
negative
but-
modes. And
But I've had people that argue that like you're supposed to discount certain like maxima of the Euclidean gravitational action. Like it's a
okay, yeah, I won't.
Right,
So
but
we're
there-
just looking at saddles now. I mean solutions to the equation of motion. We put it like that. How you then integrate over the other directions and which like you need to. It's Euclidean gravity doesn't exist, right? Because you have a negative mode. So I'm not going to mention that.
Sorry again.
It
So
is
it's
actually a
just-
saddle though. There's actually if you look at this Euclidean, if you look at the saddle points, then also if you consider fluctuations around it, even if those fluctuations satisfy the constraints, okay, then there was a recent paper recently. They showed that even then the action is unbounded below. So there was some kind of belief, or I don't know if it was a belief. There was maybe mentioned in some
But
words
it's a
that
saddle
maybe
point of path integral,
it's
right?
a saddle point of the path integral. Yeah.
Okay.
But we don't know what. My whole point was that
We shouldn't
know this
bother
path
to
integral.
write because everybody except me knows how it looks like. You haven't written your path integral.
No, exactly,
yet.
because I don't know how to define it away from far away
Oh,
from
okay.
the saddle.
I'll shut up.
No, but, yeah. I don't think we understand how to do that for gravity with a positive quantum.
I mean, you wrote it as an integral.
I did, yeah. I wrote that, but then I wrote a squiggle with saying that as g goes to 0, I'm going to assume however this thing is defined, it's defined by a sum of saddles. Which, and you can show this more rigorously in simplified models of gravity. Like there you can write an exact equation, h psi equals 0, exact path integral, and so on, but I don't know if this is, to me, it's not very satisfying. So, okay, here's this complex time plane. So to first order, this solution looks like this. So A of t is this cosh. So along here, it's exponentially increasing. When you come to the neck of this cosh, you go up, and it becomes a sine, or I sine. And so this looks here like a hemisphere, half of a sphere, four sphere. You go to the equator of the sphere, and then you glue it onto this. So this is smooth. This is smooth.
But really here, only that imaginary part is somehow non-trivial contribution of Hartley-Hawking, right?
Yeah, this thing is
That horizontal part is just what you would fill in as before.
you would just get a phase. Gives you the phase. Yeah, the phase of the wave function. This is indeed the non-trivial part. There could be and in other models, yeah, there are other types of saddle points. The ones that have been found are all subdominant compared to this one. Yeah, there's actually other ways. So, there's other saddle points, but they've been found. The saddle points that have been studied, there's no theorem, but that have been studied are subdominant compared to this one. For people I know about, it's these tau nut and tau bolt solutions. There's a class of solutions that you can also put in a manifold with no with no boundary, but they're suppressed compared to this.
And there at t equal to 0, when you go imaginary, A dot should vanish, right?
A
The
dot.
time derivative.
A,
because you have-
here A dot vanishes, yeah.
Yeah.
To first approximation, okay? So without slow roll corrections. Okay, in pure de Sitter, if this was actually pure de Sitter, A dot would actually vanish. You would get a real geometry, real Euclidean, real Lorentzian, because indeed that's the only way that can happen if A dot exactly vanishes. In the case of complex, so in the case of our actual problem with slow roll, like the actual problem that we're interested in, you can include the first slow roll correction, okay? So it looks like this. This was recently, it's actually only recently done. So you include the first correction, and you compute this function gamma of t. It's you compute it analytically, and also you compute this function phi of t here. So this just says, okay, if we look at this phi of t, for example, it has this exact form, but then we can expand it at late times. So this is the exact form everywhere, but at late times it looks like this. So this minus ht is telling you, I've chosen the convention where v prime is positive, so the field is rolling down. Okay, so we get some movement down, and it's going slowly because it's suppressed by a slow roll parameter. Then there's some constant piece, then there's an exponentially decaying real piece. But what I wanted to point out is that there's also an exponentially small imaginary piece, which is decaying along this line. Okay, so, and gamma also, I didn't go in detail of what it is, it's an explicit thing. So here in this solution, A dot is no longer 0 at any point. Oh, it's no longer 0 here at this turning point. And this metric is really a complex metric. There's no way of finding lines where the thing is purely Lorentzian, purely Euclidean. So in the actual problem, this is just a complex metric. That's it. There's no Euclidean section, Lorentzian section, but you can think of it as approximately Euclidean plus Lorentzian with small correction.
Well, but I mean, the rule for computing the saddle points and going from the forbidden region to the allowed region is that the derivative vanishes, right? A dot is equal to 0. So here you are doing something else, right? Because otherwise this won't.
Here I'm just more following my nose. I'm imposing at this point, I'm imposing that the manifold closes in a regular way. So A goes to 0, and
Yeah,
A dot goes.
that's irrelevant. It's the angle there. I mean, there you crash. I mean, if you try to do that turn at non-zero velocity, you crash in the sense that when you compute the exponential of the saddle point in the vertical axis
Yes.
plus the saddle point in the real axis, right? That's not even a stationary point, right? Unless the A dot
I don't agree.
vanishes.
I can choose this contour to be. I don't have to make this right. I can choose any.
So this is really a solution in complex T, not
Yeah.
in real or imaginary T.
No, it's a solution in. I can represent the solution with any. I'm saying this is
What is it? I mean, what is T?
T is just a parameter that's going
Yeah,
from.
is it complex or is it real?
It's complex.
It's complex. So shouldn't
complex.
that path that goes from the dot over there to the dot,
Yeah.
shouldn't that be actually a path itself determined by by requiring that the action is stationary?
No, I don't think so. It's you can take any path. It'll be a solution. No, it'll be the same. I'm viewing any path that connects here to here. I'm viewing it as some representation of this saddle point, but they'll all be exact solutions to Einstein's equations, and they're all. I'm not making any. This solution here that we're writing, if you follow. Okay, of course, if I make a sharp angle, then there's a discontinuity, but you can regularize this by choosing a smooth curve connecting these two things. And that resulting metric is going to be an exact solution to Einstein's equation with no problem.
But I think what Massimo is saying that if you consider just tunneling problem, the situation will understand how to do things like in field theory or in quantum mechanics. The other rules, there should be really turning point where you glue together Euclidean, pure Euclidean and purely Minkowski evolution, right? That's kind of.
Yeah, here,
That's
right.
not what you're doing here, right?
No, that's not what I'm doing here. I'm saying that this slow roll is introducing a correction where I can no longer do that.
Yeah, but they don't understand what it is. I mean, you
It's,
can say words saying that introduce a correction, but I have no idea what it is. Are you actually saying I can select a path, a smooth path that
Yeah.
goes from the initial
Yes.
point
Yeah.
to the final point, is a path in the complex plane,
Yes.
and I call that the parameter along that path, tau, time, whatever you
Yeah,
want,
radius, yeah.
and then I have a complex solution
Yes.
you have an integral on some parameter that is 0 at one point, 1 at the other.
Yes.
The path
Yes.
wanders around in the complex plane.
Yes.
A and phi are complex,
Yes.
and this complex A and phi satisfy
Classify
make the
version of
action
Einstein.
stationary, right?
Yes.
Or along this
Yes.
action that is an integral in d tau of some A and phi.
Yeah, which is invariant, and it's the same for every path you draw. If it's
Because you say this action
Because
is
you-
holomorphic, and
Yeah.
there's some holomorphic properties. So you're extending everything, right? You're saying A, phi. When you go from real to complex, of course, you can extend, when you make A complex and phi complex, right? Or you could say that I have the absolute value of A, the absolute value of phi. So your rule is everything is holomorphic.
Yes.
You extend it as a holomorphic function.
Yes, and it's not exactly analytic everywhere. There's poles down here, but there's no poles along this
No,
path.
there are poles in the solution, but you say the action is just a function of phi and not phi star,
Yes.
A and not A star.
I think, by the way, in tunneling, this does, like, in the most prototypical case, it doesn't happen, but in general, you do get complex paths, actually. Also describe tunneling in quantum mechanics. You get
Well, you get complex path in the variable x, not in time, right? Because typically you have a
You can also go in
limited
complex time. There's a way to go in complex time.
But is there some geometric understanding of the manifold that this describes?
It's a ball.
Well, so you have some metric, it's complex. So the manifold is not exactly Euclidean or Lorentzian.
No, but wait, hold on. The manifold is different than the metric. So the manifold, you can think of it as a ball. So the coordinate that runs, there's a real coordinate running along this curve. You can view that as a radius of a ball.
But by ball you mean
I mean,
topological
disk.
sense,
I mean,
not,
a disk.
not in the
Topology of a
metrical
disk.
sense, right? Because metric is complex, as you're saying.
It's a complex metric on a real manifold. So I take a ball, which is
But
described by a
when you
real
say
coordinate.
ball, you mean
I don't.
topologically. No,
I mean topologically a ball. Yeah.
But not the metric.
not the metric, right?
No, but I have a
Not
manifold which has a complex metric on it.
Yeah, and how is the manifold defined? I mean, what is the transition functions? What are the? I mean, you need a class of equivalence of charts where transition functions are what? Are infinity, complex, analytic. I mean, it's.
So okay, wait. If we look back at the. Like there's a coordinate running along some smooth curve you choose. Let's say it can run from 0 to 1. That would it describes a radial coordinate, and at every point along this thing there's a sphere, and it smoothly the sphere smoothly shrinks to 0. For me, it's topologically a ball. It has a complex metric on it, but it's topologically a ball.
But so there is that horizontal part of the solution. That's just roughly classical superior
Yeah, exactly.
slow roll inflation.
Yes.
So what these complex, they're small, but there are some, you're saying there are some imaginary corrections to.
Yeah, but it's both in both pieces. There is an imaginary correction here, but also there's.
Yeah, but let's focus on that horizontal piece, which we thought from the first part of your talk that we understand, right? It's just the classical slow roll.
It's a classical slow roll, but this receives an exponentially decaying piece, which then exactly reaches 0 on the boundary. So that on the boundary, you're asking that I'm computing a.
But for the observer who lives not on the boundary, who lives during that period of classical inflation,
Yeah.
what that imaginary piece? What are the implications of that imaginary piece?
Well, but okay, by the time that it's reached at the time that it reaches the observer, it's exactly 0. But
No, but there could be observers even before, right? It's a classical.
yeah, but for any, yeah.
Since you're
I'm not
computing
quite sure how to
wave
answer your
function,
question.
right? Since you're computing a wave function, you may say that the observer observes at T0. Right? That's what.
I'm not sure how to answer that question. This is a way of computing some probability, and you interpret it roughly as that, which is.
You know, it would be nice to see all this castle applied to, say, quantum mechanics in one dimension. Okay, here is quantum mechanics in 2 dimensions with a parameter in. But how would you go? I mean, how would you apply this technique of complex trajectories? So trajectories in complex time.
I think we can do it in 1D quantum mechanics.
Huh?
In 1D quantum mechanics,
Mhm.
you can study. Okay, for example, one thing that we've been studying, you can study. Well, I don't know if I should go into this in detail right now, but you can study the reflection of a wave packet off a barrier with energy smaller than the height of the barrier, and you can ask yourself, what is the wave? What is the transmitted pulse on the other side? So this wave the transmitted pulse, you can compute it with a solution that goes in the complex time plane.
Okay, but the way I do it in class is it doesn't involve t, it involves x, and then you
Going on.
complexify in x, right? You write the reduced action, which is a function of x, not of time, and then you go in the complex plane in x. But
you
here
can
you
also
want
go
to
in complex
keep
plane
t,
in time
right?
without. You can also go in complex plane in time without complexifying x.
Exactly, but I've not seen it, so I just want to know.
Maybe I should. Yeah. Well,
I've never seen it, because Landau doesn't do that way. I mean,
But here there is no time anyway.
no, but you see,
Yeah, but we
you
can
have a
write-
parametric integral where you have this complex parameter, right?
there's a path in complex time plane where it goes along the, let's say, the negative real time axis that makes the transition into the Euclidean. So what happens is the particle is coming, it's coming onto the barrier. It halts somewhere on the barrier. At that point, you go in complex time. Solution remains real. The barrier gets inverted. It goes onto the other side of the barrier, comes on to a halt on that side of the barrier. Then you continue back in real along the horizontal time axis. But the time contour looks like this. And this is t. And the solution, here's the potential flat, there's some bump here. So what happens is that the solution comes with some energy E, which is smaller than the height of the barrier. It comes to a halt here along. This is what's happening here.
And so there you comes to a halt, an exact halt.
There it comes to it. Yeah, in this case, it's real, and yeah, in that case, it's a real.
But so when we're calculating delta rho over rho, it's in the standard way, we look at we're quantizing around the classical solution on the horizontal axis.
Yeah.
So the fact that you have these complex corrections, so that's
But they're exponentially.
How does it affect this?
I think that no,
Delta
they actually
rho.
don't affect. You can calculate delta rho over rho by looking at fluctuations around this saddle, and you'll get the same answer. It's an exponentially small correction here.
Well, it's exponentially small, but you can keep it. Like, let's just for the sake of.
But you can. You get what when you
So
compute,
that's just
let's say the
small
wave
complex,
function.
right? So
But when we compute the wave function we compute the wave function for those fluctuations, we fix the boundary values here to be real ones. When we compute, let's say, the wave function of zeta,
But
they're real here.
Why are we arguing about anything whatsoever? You are working in mini superspace, correct?
No, I'm just
this
looking
is
for a
just
saddle.
quantum. This
You
is
can
just
say
quantum
mini superspace,
mechanics in 2 dimensions.
no,
I'm not
but
even
one
doing
can
that.
add,
We are
one
just
can
trying
add
to
other
understand
modes,
that.
right?
I'm not even doing. I'm not even doing. I'm looking for an exact solution to Einstein's equations, and you can say I'm not quantizing around that. I'm not a.
No, but it is quantum mechanics in 2 variables, correct?
You can view it like
No,
that, but I'm not doing the full package.
It's- look,
Or even less.
This is classical mechanics with complexified variables.
Yeah.
But indeed, the thing that threw me off, and always throws me off, is that you are complexifying in the parameter, in t, instead of complexifying in the field.
But does
This
he
is a
compute
standard-
something
doesn't matter.
well defined?
Standard.
Does not he compute something well defined? And
I'm
then
using a
his
trick-
complexification is just a mathematical
Yeah,
trick to
exactly.
compute it.
That's
That's
exactly
all
So
there
I'm
is.
just trying to understand, there are 2 ways to do complexification, and that's what I'm trying to understand. There are 2 ways, not one, right? You can complexify in the variables a, phi, or you can complexify in the parameter t,
Right.
right? So the one way is to keep t real and complexify in a and phi. The other way is to complexify in t. These are 2 slightly different ways. I don't know if they are the same secretly, but that's what
Sounds
Don't
Yeah,
they
they are
get the
the
same
same.
answer if you do it in
I think they are the same
one-dimensional
secret.
quantum
Yeah,
mechanics?
exactly. Even in that case, we'll have the same problem.
Well, I think they
And
are
he
the
claims
same
they do.
It's the same thing.
I think they are the same thing.
It's the same thing.
Yeah.
Okay.
Okay, so let's continue with it. Okay, so okay, whatever you may think of this, there's a very big. There's many.
Sorry, because you showed these corrections, which you said, oh, they were calculated only recently. But what,
No,
what is the
actually-
meaning? What is do they have any meaning? Do they have any physical?
No, it doesn't change anything about the answer. This is an exponentially decaying piece. Once you arrive here, there's then, if you make the boundary values, a and phi, exactly real here. They are exactly, with no corrections, they are exactly real here. That's what my wave function is computing. It's psi of a and phi, where a and phi are completely real. That's what this solution does.
Sorry, how does it work? It doesn't.
It works when you get up to this point. There's an additive constant that is of this size that makes it exactly real here. This is
So why did you bother calculating these corrections? Do they have any implications? Do they have any meaning?
okay, let me.
Log 2 I have
Well-
seen before.
These corrections.
Yeah. This complex, this imaginary piece.
Do they have any meaning? They're going to become important for something I'm going to say pretty soon, which might confuse even more. But yeah, I'm sure it'll confuse more. So there's an exponentially decaying imaginary piece here, and that's going to become actually important soon.
why don't you go on and then we can see where you're going.
Okay. Yeah. By the way, this approximation also fails at some point. So this can become order 1. So you're doing this lower order expansion, but there can be a secular growth here. In large field, for example, in quadratic inflation, this becomes order 1, and you have to go through to another description, which I did here. Anyway, we need to come back.
Sorry.
It's already 10.
Yeah, you have about 15 minutes.
Okay. One second. I'm not even gonna go ahead. Okay. Here's okay. I wanted to give some broad motive. Even though this gravitational path integral, we don't know how to define it in full. There's some motivation to still use it in the semi-classical limit. I wanted to mention some examples from ADS CFT, which I won't do. One is about the Hawking-Page phase transition, but I'm gonna skip the motivation. So we have these complex metrics that we've been talking about, and they're strange. As you see, we got confused also. So okay, so the idea is that we have these complex metrics on real manifolds, but they're complex, and so. The idea. So how can we distinguish between good saddle points and bad saddle points? So I'll describe a criterion which was formulated in this paper in 2021, building on earlier work. So let's consider a simple example. Here I have the metric on flat space in d plus 1 dimensions. The contour that I take for R goes from 0 to infinity, and this is just the metric on flat space. I think we all are okay with that. Maybe this is where I should start. But then what we can do is complexify R, the radial coordinate on the plane. Okay, to make it a curve gamma of L, which is a smooth curve, and make it run in some other way, going still from 0 to infinity. So the metric now becomes this one, where gamma prime is complex, so because it's the complex derivative of this thing. And also this R coordinate is now complex, moving along this curve. So that's what I mean when we complexify a metric. In the same sense, the Hartle-Hawking solution, the one that we discuss, is a complexification in this sense. So because it still runs from 0 to infinity, it's topologically still the plane. But we could do different things. We could also allow it to go in a circle. So now it would be topologically a sphere, because the coordinate is coming back, but it's a complex sphere. This metric, it's a complex metric on a sphere. Now this thing is strange because it's flat. It's Ricci curvature vanishes completely. It doesn't satisfy Gauss-Bonnet, so the usual theorems about this metric in, let's say, in 2 dimensions, they don't hold. It's a flat metric on a sphere. It's already weird. But it's an exact solution to the Einstein equation on the sphere, complexified one. You can also start drawing other stuff. For example, this kind of, you imagine that there's 2 copies of R of the plane, which are connected to each other via a complex transition. This also is a flat metric on this space. You can draw a pictorial like this. This is complex transition, and we can make this smooth but with compact support, so it's an exact solution. You can upgrade this to this kind of, well, you could call this a wormhole, some transition between 2 parts of the same space. That you can do that via cutting and gluing procedure. So you just take the solution that we had, you stop here, you imagine some other copy, and you glue this part here, and then identify in the rest of the plane. So that's a way of constructing this kind of solution. Now these things don't make much sense, at least not naively, because they have 0 action. Ricci is 0, the boundary term is 0, the action is 0. They cost nothing to produce. So then you would say, oh no, so now flat space is unstable. Of course it's not. But to say that these kind of things are somehow, we don't want to consider this. Okay, but on the other hand, some saddles are probably okay. Okay, so, and this is, it's speculative, but it's a proposal for some saddles that could be okay. How to determine them is to consider some general complex geometry. So it's a real manifold with a complex valued metric on it. And the proposal is, in the first instance, put a massive probe scalar on it. No back reaction, but we put the scalar on. And then we're going to assume that we can compute correlation functions of this scalar by performing a path integral over real valued configurations. So now we're doing path integral d phi over real value functions here, scalar, on the manifold, we're weighting it by the action. Whether this is IS or S, it doesn't matter. The conclusions are the same. And the action here is just the kinetic term for the scalar and the mass. Now this thing is going to be, at least for a mathematician, manifestly well defined when the real part of this action is positive. Okay, so the real part of this exponent is positive, and we want that to hold for all field configurations and at all points. Okay, so we need the real part of this thing for a real valued phi to be positive. And we can argue about the real valuedness of phi, but we can come back to it later. But we're asking in this case to be phi to be real valued.
Is that to make it well defined, or is there some other?
If you allow for a general, you can choose some other country, you get another condition. But if you allow for anything, then you won't get anything, because then you can always make something convergent. If you have a Gaussian, you're integrating it, you can always integrate along the right direction to make converge. Now we're going to choose a specific direction. Otherwise, we'd have nothing. Okay, so we want the real part of this thing to be well defined. Now, for that to happen for all phi, well, we can take constant phis, or at least in some large compact region, constant phi. So then this term is irrelevant. So that's just asking that the real part of the root of g is strictly positive. Of course, this is a convention, so we can always choose the sign of the square root to be either one or the other. Here, we're choosing it to be the positive sign, but we're saying this condition is telling you that you must be able to make this choice. You go on your manifold, and at every point, well, basically the determinant of g cannot be purely imaginary. Sorry, it cannot be it cannot be a negative real number. This cannot be negative real because then I could not make I could not make this choice. So this is, in a sense, it's a convention. It says we're going to make this convention, but we have to be able to make that convention. So that g can never be negative real. So for example, we can never be exactly on a Lorentzian line. That would mean it's impossible to do that. So we have to be always slightly deformed away from Lorentzian. Yeah. Good. So the second criterion comes from considering this piece. So we can also consider, so we consider this piece now. And it's asking for this thing to be positive. Now phi is real, so that just means that this matrix is positive definite. So I mean the real part of each component here that defines a matrix, the real part of that is positive. Positive definite matrix. Okay, so if that's true though, then we can diagonalize G by a real coordinate transformation. So we have a manifold with real coordinates, we perform a real coordinate transformation, but we bring the complex metric into a diagonal form, which has complex elements on it. But the fact that this is positive definite allows us to be able to do that. And to see that, we take the real part of this thing, which is positive definite, and it's symmetric, so we can write it as S transpose S, where S is real. It also has some imaginary piece. And there's simple manipulations that you can show that you can actually find a real matrix, a real change of coordinates, P is real, such that this goes into a diagonal form. This is what the basis change looks like in general relativity. So in this basis, I won't go over details because I don't have time. G, inverse of G, but hence also G, you can find a basis in which G is diagonal. Now, Witten told me you're not allowed to call these eigenvalues, so I won't make this mistake. It was very embarrassing. So these are not eigenvalues, okay? They're just things on the diagonal. I think the point is that you can rescale. You can rescale by doing a coordinate transformation, a real one. You can rescale them, okay? So they're not really eigenvalues. You can't rescale, but you can rescale those lambdas, so they're not eigenvalues. Anyway, there are things on the diagonal. So we want this thing to be positive definite. Now we brought it into diagonal form, and now we check. What does this mean? So this guy just puts in 1 over these lambdas, okay, on the diagonal, and then we're multiplying by the square root of the determinant. Okay. Now we write all this out. So all that matters is the phase, because we're looking at the real part. This radius doesn't matter. So we get on the diagonal there will be arguments of this type, where we have a single minus sign inserted. The minus sign is inserted because, well, we get a 1 over 2 times the argument from this piece, but then we get a minus the full argument from each one of these. Okay. So we just get 1 minus sign inserted. So now the conditions are these ones, where these things lie between minus pi and pi. We put it in a single minus sign, which in all of them. We also have this, so that means that also the sum without any minus sign lies in the interval, lies in this interval. Now, You can impose more conditions by putting, I won't do it, but it's very simple. If you put more general free p-form matter on here, for any p going over a range, then the condition simply must.
Sorry, what is the condition on the p-forms? Because
They're real valued.
they are real valued, even though if you
Replace it by the metric.
and if you take, say, a mu, one form, and you come a0 may go into I a0. So that's
A0 may go into A0. No, I'm asking for, no.
So
The forms that I'm putting on the geometry, they're going to remain real valued.
which
Yeah, this is the essence.
not obvious. That's the right
Not obvious,
description.
but it gives you something.
It's not true in Janssen, for instance.
Okay.
When you do, complex saddles.
I guess we didn't really know about that, but yeah. Right. Okay. Yeah. Again, it's a proposal, but it passes some really non-trivial checks that this makes sense. Okay. So. Okay. I should probably think about wrapping up, but
Because your field phi is not real, right? In the saddle.
no, but that I view as the background. Yeah. No, look, I have a background which can involve other fields, and what I'm gonna put on there is probe matter, put small fluctuation that doesn't backtrack, and I'm gonna ask intuitively for that thing to be well behaved, so for these things to converge. But I'm not allowing back reaction. The phi that I had before backreacts, but I'm not considering that. Yeah, I'm not considering that as a probe. That's part of the background.
And the probe is real because you decide.
The probe is real because we decided to. Yeah.
But there is no real deep reason.
No, really not. And in fact, that's how you could criticize this. Yeah. I think that's one of the main things. So it's lacking some physical motivation, which I'm going to mention. But still, there's some non-trivial checks that it passes. And for example, with examples from ADS-CFT, which I probably won't get to, but there's some non-trivial checks that this actually does make sense. Okay, so the procedure is given some complex metric, you put it in diagonal form, okay, by a real coordinate transformation. So you do that if it's not already diagonal, and also if you cannot always do that. But you do that, and then you check this condition. That's the procedure. And also, it has to hold at every point on the manifold. So this is a condition that holds along the whole. The solutions that we just discussed, that holds along the whole contour. It has to hold at every point. It's a point-wise condition. Okay. Let me just. I mentioned the examples that we discussed. This thing is allowed. Why? Because it's just the Euclidean metric. All the lambdas are real, so the arguments are 0. So the sum is 0 and it's smaller than pi. Great. It's a Euclidean metric. It's allowed. This depends, because I drew something arbitrary here. But this thing is always not allowed. The reason to see it is that at some point, any topological shape, any shape like this, like a circle, at some point you have to go down. And in that direction, gamma prime is proportional to minus I. So the square is a negative real number, and that's not allowed, because this will contribute already pi. This can contribute more, but at least it's pi, so it's not allowed. Never. Nothing like this is allowed. Same thing with the wormhole. Okay. Now let me quickly go, because we can. I'm very happy to continue chatting with anyone else that's interested. So let me go to the conclusions. This was a recap for people that didn't follow anything. So maybe I should recap here. That we're trying to evaluate a gravitational path integral in its limit, in a semi-classical limit. We don't know precisely how it's defined, but we're going to assume that it receives its main contributions from the vicinity of saddle points, mainly from the saddles. That's what we discussed. Which saddles are relevant, though? It depends on what the theory is. Far away from the saddles. You really need to know. You really need to know the full theory to actually answer this question. But we don't know it. But the idea here is that we may already be able to tell which saddles are definitely not relevant. Of course, it's debatable whether this is the correct criterion. That's the idea. And you look at that by trying to integrate over the other fields while fixing the gravitational part and other parts that may backreact to their saddle point values. Okay, of course, when we have a full understanding, this may become moot, or maybe it'll remain as a simple way to check for something that definitely doesn't make sense. Okay, so that's the condition. So this is definitely not allowed when this is ever greater than 8 to the pi.
But what is the answer? Is there going to be an answer
To what the actual criterion is?
to whatever physical question you are trying
Yeah,
to
so
address?
let me go to the answer. Okay, so the answer is that we had this these complex metrics that we thought might be relevant to generating this wave function, which we can view as some probability for initial conditions for inflation. We have these complex metrics that we discussed. Now you can ask, these things have a complex decaying, I mean, they're complex, okay, like we said. So do they satisfy this criterion or not? That's the question. Okay, the answer is it depends. And there's a formula, which is this one. Okay. And
sorry, just go to the previous formula.
Yeah.
This gamma is arbitrary. So
I'm allowing, okay, so I have an A of t and a phi of t, which are defining the whole complex plane. Now I'm going to draw a curve which goes from here to here, which is some gamma indeed, gamma. But I'm going to ask myself, does there exist any gamma? I'm going to be very liberal now. I'm going to say, if I find some gamma such that the criterion is satisfied, then I'm going to call this an allowable representation of this saddle point. Because, like we said, you could choose some other representation, which you could or could not view as the same solution. But I'm going to already be content when we can find one representation of the saddle in terms of some such that this is satisfied. Now, you can answer that question in slow roll for all of the inflation models. It's an answerable question, and it boils down to this integral being smaller than 1, up to slow roll corrections.
now, in your background, you also have phi, right?
Yeah, phi only is important because the condition on the thing being allowed is only directly on the part of the metric, but it receives a back reaction from the phi, so it enters implicitly like that.
But why it's only on the metric? Because you may say that the functional integral should also has a piece that's proportional to the fluctuations of phi.
Yeah, that would
So
be
there
maybe
would
an
be-
additional condition.
Yeah,
In fact,
a piece proportional to, for instance, the second derivative of the inflationary potential, right? Because that.
I think you could then but it would introduce more.
But also these real perturbations, they may be coupled not just to the metric, but to the phi. For instance, there will be term like phi squared, chi squared.
Yes.
And phi has a background. So
Yeah. So then
that
I'm
is
not
what
just, yeah.
So in principle, that would be the way to
Yeah,
change
that
also.
would be a
relax
change,
this
or to probably make the condition stronger. No, I'm asking for more things to be
condition.
bound.
No, it would be weaker, right? Because it will be no condition just on the metric, but metric plus phi, right?
Yeah, but if I'm including additional interactions, those things.
No,
will-
but because you're looking at square root of minus g chi squared term.
Yes.
But now there is square root of minus g chi squared plus square root of minus g phi squared chi squared.
Okay, that could change. That would
and
change.
phi has a background, so in principle you
It
can
could
get
change
very
the
different-
condition.
Yeah.
Agreed. Yeah. And I think
Why do you have v prime of phi star under the integral?
it's a new formula. So it's a new formula. So this is just what I didn't explain how to get this, but this, yeah, I would love to explain. But this is a formula that looks a bit familiar, but not really. So you're maybe familiar with the formula that goes like.
I think he's asking why it's inside the integral.
It's just because this is why this is inside.
This
the
is
integral?
just a
I
constant.
normalized. It's a constant. Yeah. Sorry. Okay.
Or you just wrote it like this.
I really
For
am because
fun.
it's a nice way to write it. It's very nice
Oh,
because the reason is
You
that the
claim
thing
it's
is
a nice way to write
yes, I
it.
explain.
Okay.
And why is that? There's many ways to write a formula, no? Okay. But why it's nice is because this is a, like you say, this is also constant. This is a factor which is small. It's still rule suppressed. Okay, it's v prime over v. It's square root of epsilon. So this is a small factor. This thing is normalized such that when I start integrating, I integrate when my phi is near phi star, which is the beginning of, you think of as the beginning of inflation, this integrand is normalized to 1. That's why I like it. So you start, yeah, I'm integrating a function. I'm integrating a function which starts at 1. Then depending on how this thing behaves, and this can either grow larger than 1 or not.
But for us peasants, this phi star, for example, for m squared, phi squared, what is it?
Okay, so I was going to show it here. So this is this is not m squared phi squared, but it's the same thing. Yeah. So we choose some point at the end of inflation, which is here. Okay. Now now you can change phi. You can move phi star up the potential, and then the value of this integral is going to change. So when phi star is close to the end, this integral is very small. And this is already
And
small.
you claim phi star when it becomes 1 is the true beginning of inflation?
Phi star, this phi star depends on the boundary condition that we put, right? So we I had another picture here. This is what the saddle looks like. We have some phi here. Phi star is the one that's determined by the size that the size that we put on the final slice. Depending on how big that size is, phi star is gonna
So phi
change.
star is
It's
not a
function.
characteristic of a potential. It is
Phi star, it depends on the
on
size of the
A
boundary.
also. On A also.
On
or
A.
what?
There's only two things that anything depends on. It's the final values, phi of A and phi. And these are final values, phi final, phi final.
So therefore,
Phi
it
star is a
has-
function of these two things.
if my purpose is to compute whatever n and r, your thing is useless for me because I don't know what is phi star, and therefore I don't get any limitation on my potential.
I'll get a
True or
limitation
false?
I will get a limitation, but I'll show it in a minute. But the limitation comes from the following fact that it will. So if I I fix phi to the end of inflation here, and what I can do I can ask for this slice to be extremely large. Let's say 60 equals large, so it's e to the 60 over h.
Or 70 or 100.
Whatever you want, any value. This. Now I'm gonna draw. Now do that. That boundary value has a unique infilling, which is real, which is a solution to the equation of motion, which this thing.
So phi star depends on the number of e-folds.
Star depends on the size that you put on your final boundary. Let's say it's 60 equals large. Is e to the 60 over h being this h.
But you will explain this, right?
Well, I mean, I would love to explain if we have time, but so the procedure is I fix a size of the universe here, which I think of as being the end of inflation, where phi is at the value of the end of inflation, where the slower parameters are 1, order 1.
So this is epsilon 1, phi m.
Epsilon is 1. Or eta,
Phi
whatever.
star depends on the number of e-foldings.
Phi star is a function of these two, of these both.
These two, I don't know what it is. I know the number of e-foldings. Suppose I am God, I can measure the size of the universe,
Yeah.
then I know the number
and phi
of
star is a
e-foldings.
function of that
Or
amount
of the
equals.
number
And I
of
can tell you
equals.
which function it is. How you get the function is in the following way. You take this, you go backwards in time by slow roll. Does this make sense?
So,
It's
so
okay?
far so good.
You go back until A is order. This is how you can think of it. It is of order 1 over h.
Okay.
Because you go back until that time. The phi that achieves that, where A is 1 over h in the past, that phi is phi star. Up to a slow roll correction.
And therefore you can turn this thing into predictions for inflationary
Yeah.
parameters?
Yeah. Because let's say I had 60, because depending on the potential, this complex solution is either going to be allowed or not by this criterion. And you can very sharply say, it's a completely well-defined mathematical question, when is this drawing, which is this complex solution that we talked about, when does this pass that condition?
But how do you interpret it if it's not allowed? That the probability is 0 for that?
That there is a subdominant, yeah. Bill, for now, I don't know the answer to that, but it's at least
It's
that
very
is
suppressed.
yeah, it's exponentially.
But what is the
I don't know how to answer
practical implication? Suppose I select one of the
Okay,
potentials.
Here, look here. This is the maybe this is better. This is the practical implication. So this red, what you haven't seen it before, is because this red are things that don't pass the criterion. I can explain exactly what it means.
Oh, so for each potential you actually cut off
Yeah.
certain.
Well, I draw exactly what this means. So let's take a point here. This point. That happens. Remember, it's this model. Some lambda. Okay, it doesn't depend. Nothing depends on lambda. 1 plus cosine of phi over f. Okay, so okay, this is the potential. Looks this is not a good drawing, but it looks roughly like this. Okay. Sorry, the minimum should be a minimum drawing is very bad. Sorry. What's that? Okay, that potential looks like this. There's a particular f that corresponds to going up. Let's say I'm on any point here. This corresponds to an f and to some amount of e-folds that I'm allowed to inflate. Okay, so let's say, just for the sake of some point there, this is like f equals, let's say 2. I don't know. F is 2, so we have a potential. But also the horizontal distance tells me how many e-folds of inflation am I considering. So let's say inflation ends just before I reach this minimum. Here epsilon becomes 1, which depends on f. Okay, so epsilon is 1 here. Inflation ends. Now I consider some inflationary trajectory which has some fixed amount of e-folds. So this trajectory will correspond to A. There's some phi star here, which if I inflate along this patch, I get a size A, which is, let's say, e to the 55 over h. H of phi. This is concretely what it does. Does this make sense?
Ah.
A point on this potential corresponds to a point on this plot corresponds to a potential, and also to some inflationary trajectory which has gone through some amount of e-folds.
The higher you start, the more e-folds you will get.
Oh.
But in classical inflation, all points high enough to give you 60 e-folds and higher, all acceptable.
Are all
but
acceptable.
now you are saying
And all
no.
these points would be green. All the green points would just be acceptable because they're just inflationary solutions with some amount of e-folds and some model.
Yeah.
Okay. Now, to each point on that plot corresponds some final boundary condition on an inflationary potential. Okay. Now I'm assuming that that thing is that final boundary condition is prepared by this complex solution, which is approximately real, but then goes into imaginary time and smoothly caps off. So there's a real boundary condition which corresponds to a point here with a potential. I fill that thing in with a complex solution that we discussed, which is completely explicit and known. And then I check, does that thing pass this criterion or not?
Of acceptability,
Of acceptability
of
for
this
this complex
complex
solution.
metric.
Yeah, and this is a completely well-defined question. There's and the answer is, in this way of looking at it, is this. The red is not allowed, and the green is still allowed.
So you have explained the smallness of R,
No,
for example.
I don't want to claim that. I don't want to claim that the striking thing about it is that it does anything like this. No, that maybe you would have expected everything should be allowed, nothing should be allowed. It could be something radical, but here it draws some fine line in the middle, and seems to indeed not like inflationary potentials with, like, for example, m squared phi squared. You see, it's complete. It's not allowed. We can explain it via the formula that I gave, but
How much different would this look if you cut off all those potentials at some super Planckian field excursion? If you said the inflatonic.
like m squared phi squared, we would already not be able to do anything already.
Yes, that's true. So one of
We
those.
wouldn't be able to get a lot of inflation.
Right. So you're saying it would look quite different.
Yeah, here's something that it would look very different, is that if you, this is a thing that you can show with the formula that I gave, is that if you take any one of these potentials, and you consider, let's say, your favorite amount of e-folds, let's say 60, then after that you cap it off with a very smooth, with a plateau, which plateaus, let's say, exponentially quickly. So then if I start the inflation there, it'll produce many more e-folds, right? But it will always be allowed. You can always cut it somewhere, put a plateau on it, and then start the inflation there. That will lead to something that is allowed. But in any model, in any specific model that you have, without manhandling it like that, you have any smooth potential, you can just answer this question.
So you can
This is the answer for these potentials here.
And your assumptions is K has a definite sign, the curvature is the K in Friedman.
The K in Friedman is positive. Yes, I'm a sphere, always I'm a sphere, because I want to have a compact solution.
So wouldn't that rule out the models that come from Tunnel? I mean, you wouldn't be able to do this analysis.
No, I wouldn't be able to do
models
that.
come from
Yeah,
Tunnel.
but this Hartle-Hawking state doesn't apply to those. Doesn't calculate the probability for open universe. Yeah, that's all different. Yeah, so that's the conclusion. And I don't claim that this is okay. So maybe I should also conclude by allowing you to think I'm crazy. So although neither of these things, as we saw, they're not on a firm footing. Okay, but they're mainly there's examples that show that we're getting something right with these things. For example, this Hartle-Hawking solution, it's a complex background, but you can consider small fluctuations on top of it. And when you compute the wave function for small fluctuations, you get the answer that we predict with standard methods in inflation. So you get the NS, you get all the standard inflationary predictions. So as a background, it seems to be fine. However, when we compute the probability for the background, we're getting this curvature puzzle, which I didn't get into, but there's definitely some puzzling things, very puzzling things about it. There's also puzzling things about this criterion. On the other hand, there are some examples that show that it's getting something right? Okay, and I think these things invite us to understand it better, and definitely because if you think about if you take them both seriously, that leads to something quite radical like this, which is, I'm not going to claim that this predicts the smallness of R, but it shows that something interesting comes from these two things. And I think it's a motivation to understand both of them better, if they're getting something right. If for the Hartle-Hawking proposal, maybe a resolution could come from looking at connected contributions to the density matrix of the universe, like something we're working on. And for this criterion, I think it will be useful, if you want to put it on physical grounds, to consider the dynamical stability of probe matter on some complex background. So here we're looking at some integral, but it's unclear what if this implies that this doesn't necessarily have something to do with the dynamical stability of something. Maybe that should be maybe these two things are related, but this will put the condition on it.
But the logic of it is really perverse, because you are saying in the process of computing some path integral, which you don't really define because you say you don't know what it is, you pass through some complex matrix. Then you say some of those complex matrices through which you pass are no good. And all of a sudden you say, which means that these potentials are not allowed.
Well,
it only means that you cannot compute it by your methodology, right?
Yeah.
Well, no, you might say it means that the probability is very, very suppressed, because what would have been done.
So if you cannot compute, you can, like, what is it? If it's not infinity, it's a zero.
No, when you do an integral by saddle point, you often find saddles that apparently contribute and would dominate, but they're actually not allowed.
In fact, here,
They're
I
actually
have
not
this picture.
on the contour.
I had a picture actually.
Right. Yeah, you didn't have a chance
But I
to see
didn't.
this, right? Yeah.
Well, this
So-
is for the people that didn't.
Yeah, there are plenty of examples like this where it looks like there's a saddle that should be the dominant contribution, but in fact, it doesn't contribute at all. And so the answer is
But
So
when it
what-
doesn't
if that were the
contribute, you
potential,
conclude
what would
that
be
the
the
probability is small.
much smaller than the one you would have predicted from the
If the saddle existed, there would be a much larger
Yes.
probability in some
If it contributed,
If it
it
contributes.
exists.
It exists,
The
but-
thing exists, but
yeah.
actually maybe this isn't good. I don't know if you have time.
Well, maybe we should
maybe we
thank
can
you.
conclude it.
Thanks.
I was going to ask you along those lines. There's the sign, right, between Vilenkin and Hartle-Hawking.
Right.
Which one of those?
So Hartle-Hawking gets chosen by this, but sort of by definition because of this square root of g.
Yeah.
So we impose that the real part of the square root of g is positive.
Uh-huh.
And if Vilenkin, you make the opposite choice.
Right. Okay. So but I guess my question was this: as you approach, let's say on that plot, a point that's excluded. So you have some probability that you compute, and you're in the allowed region, and then all of a sudden you're in the non-allowed region.
Yeah, it's the square root of g that's changing sign necessarily.
And
That's
is
the
it-
condition that's failing.
Okay. Is the probability getting small or large as you approach the point where you're going to exclude the saddle?
The probability for the
Yeah, like you have some calculation of you have the square of this wave function. that you
yeah
calculate.
the probability. But we're going through different potentials. So,
Well, can't you move? I mean,
Because
Yeah, you can-
unless the answer to Matt's question is positive, the interpretation of your result becomes fuzzy.
you see what I'm asking, though, right? Because normally when you exclude a saddle,
Yeah.
the answer is smooth after some.
let
small
me actually. I think I think the answer is that the probability is becoming large. So as you go from the allowed to the not allowed one, I think the probability would be increasing in that direction.
Okay. Yeah, because in the simple examples that I know,
Yeah,
when you cross the Stokes line, it's always at the point that
it's the
you cross
subdominant one that goes away.
Yeah, at the point that it disappears, it's always subdominant, and then later it could have become dominant if it still existed, but it doesn't.
But now we only have one.
Now we only have one.
There's only one saddle, so
true.
it's there and
Yeah,
disappears.
yeah. Okay.
There could be other. Well, there's also other saddles actually that are known,
Mm-hmm.
and I haven't checked some, but there's other saddles that are in this whole.
But when you say one saddle, these are complex, right? So the conjugate, of course, the saddles will come in pairs.
Yeah, but true. But the conjugate pair doesn't always contribute. Right? I mean, it's not like if one contributes, so does the other.
So when you say does not contribute, you mean it's not on the pivoted integration contour?
Right. Yeah.
Which we don't know.
Well, in this case, we don't know, but it's like I'm trying to make an analogy between this condition and whatever that thing is called, the Lipschitz thimble or something. But
Yes.
Yeah.
Yes.
So. Yeah, I'm just
I mean,
wondering.
about the complex conjugate saddle, that would have think that would have the opposite sign of the square root of the determinant of G.
I see. So it's without
You just
that
already
relation.
rule. You just don't consider it.
But
Or if you do consider it, then you would be forced in that saddle
Choose
to make the
the
same to make the same choice. So you would lead back to the original saddle. These sort of these things should be.
But so your the KSW criterion selects the sign of Hartle
Yes.
and Hawking.
Yes.
right?
Yes. It selects it selects that sign because it's the usual calculation that the Euclidean action of the full sphere is negative, and that's the sign that you get.
And that's also the sign that makes the fluctuations
Well defined.
well defined.
Yeah.
So what's the problem with inflation and with these signs? Is it
The problem is that the Hartle-Hawking solution favors, if you look at the formula, it just favors no inflation. It's a big problem.
You should start at the bottom of the potential.
Yeah.
That's the most likely origin.
Yeah.
But here, this problem is solved by this method?
Well,
or not?
good. No, actually, no. So I said, no, well, I didn't have time to go. So no, it's not solved. But I wanted to say one thing. Now you're asking again.
So, what's the point of computing probabilities if you should start from the bottom anyway?
Yeah. Now we can still ask the question. Let's say maybe
Suppose
it's not,
the
maybe it will be
inflation did happen.
Yeah,
right?
exactly. Yeah, maybe you'll not be satisfied. Maybe let's say at least 6-fold inflation happened. We can still ask which inflation.
Right.
But about this puzzle, I want to say one thing. Okay, it's and it doesn't hold for every model. It's model dependent. But let's consider this model again with f equals 5. Okay, so it's super Planckian. But let's consider f equals 5, and this is the result for the allowability. So. Okay. So this is my this is still pi f. Inflation ends around here just before we reach the minimum. This is phi end. And now, so you see phi star, it's around 15. Okay, so that's around here. No, phi f is around 15. And I put phi star, let's say here. And then I move it from. We should view this figure from 15 back to 0. 0 would be starting on top of here. On top of here, there's classically infinitely many e-folds of inflation because the thing is exactly flat. So very close here, it goes to infinity. Up here, it goes to some finite value. Okay, now what you can do is you can take phi star, and you can check, and you can move it up here, and consider trajectories with more and more e-folds of inflation as we move the beginning of inflation up towards the maximum. And this is what this integral formula, how it looks like.
This is the thing which should be less than 1.
Which should be less than 1 for to be allowed. If you now you see that there's a very small, even actually, yeah, that formula is assumes slow roll. So even here it's not exactly valid, but from here it actually starts being valid. So how to interpret? So yeah, this piece is not exactly trustworthy. It's just this formula, but it's not the exact answer. It's valid in slow roll. So here there's an order 1 amount of e-folds, goes up very sharply. So. And then there's a large region here, which is not allowed. Of course, it depends on f. Okay, so I'm not saying this always works. But then, when you have enough e-folds, you transition into a region which is allowed forever again. So this would be not allowed, and this would be allowed again.
So you either have no inflation or a lot of inflation.
So you say maybe, yeah. So my interpretation in this thing is that in this particular.
But do you get enough e-folds?
Depends on f. Depends on f.
For this particular f,
for this particular
phi star
f,
is less than 4. Do you get enough?
If
Phi star should be less than 4, correct?
Yeah, then you get 42
It's
e-folds.
42. Yeah.
Oh, okay.
In this
You don't
case,
get enough.
I chose equals
Okay.
5, but it depends on f, and you can choose. So in this model, you can say I want to compute the conditional probability that the universe is at least 1 Hubble size. Okay.
So the most likely thing though is just producing a big universe that didn't inflate, and then after that, the next most likely thing is that
The big universe.
yeah.
No. This phi star also.
Oh, because
No. The size is varying.
Fine, that depends on A. You're right.
So either you put a very small universe,
Okay.
but once you're above a certain threshold, let's say you can put some observational bound on that. You can say,
Yes.
I want to have a universe which is at least as large as 1 over h. Then this tells you no, that's not possible. You have to at least something that's as large as.
Okay, so given
e to the
that,
42 over h.
given that we don't see any spatial curvature,
Yeah.
can't you just throw away the favored thing in Hartle-Hawking, which would be a universe that's dominated by
By nothing.
curvature? Yeah.
Yeah.
and then you say, okay, you have to have had inflation, and so therefore you must.
In this model, then
in
you
this
would have to
model,
have had a lot.
Yeah.
Okay, that's why I think it
Right.
touches upon this puzzle
Yeah.
in
Alright.
this sense, but it doesn't solve it in every model.
And eternal inflation also is allowed.
Excuse me?
Eternal inflation.
Here there's, yeah, I'm not even discussing, yeah, it doesn't enter in that, eternal inflation hasn't entered here. Looking at classical saddle points, we're not considering.
But the meaning of probabilities remains unclear.
Yeah.
Everything is just as unclear as before.
Yeah, that part I'm not
It's
solving.
just that-
We're introducing one ingredient, which is saying we have these strange complex metrics, which we're very confused about. But there's some proposal now for which complex metrics make sense and which ones don't. Now I have a large playground of complex solutions, all of these, which are probably the biggest collection that I. And now we can distinguish which ones are allowed and which ones are not.
But you can, if